Okay. Just most people are doing pretty well with this, but wrote this down for a reminder because some people are just a little bit fuzzy on this part. So if you're getting these, if you got the first one, you probably got the next few. So you don't really need to pay any attention to what I'm saying right now. You just keep working. I'm just going to do the first one. If you know how to do that, you don't need to hear what I say. Although if you find my words irresistible, go ahead and listen. Okay. Now, you can say log base 2 of 4 equals x if you want. And that's equivalent to saying that 2 to the x equals 4. And you know, the 2 okay. Another way you would know this is if you have the graph of the log function. This involves a log base 2 function. Which has a graph that looks like this. Then, of course, the log base 2 of 2 is 1, the log base 2 of 4 is 2. It's right there in your graph. It's right here on your table. The log base 2 of 4 can be found in a variety of ways. Okay. If you think about the table, you can figure out what the log base 2 of 16 would be. If you use this, you can figure out what the log base 2 of 16 is. Okay. Your graph isn't going to particularly help you unless you extend it out. But x equals 16 is going to be one of the values in this graph if you continue converting the graph of the basic exponential function. In other words, you take the basic exponential function out a few more numbers. Okay, you go from -2 to 2, then maybe you go to 3, 4, 5, 6, and you get values of the exponential function. So those are all ways you can do this. I'll talk about those when I talk about this. Talk about some of those ideas, just to make sure we have a pretty good grounding on the basic exponential functions and logarithmic functions. Okay. Now, make very clear. Here are your equivalences. If you let A be, if A is x and C is y, that's just y equals b to the x. And the inverse function would then be log base b of x equals y. You just flip your x's and y's, and you have your inverse function relation. So this is just an expression of the inverse function relation. So kind of think about that, but one way or another, make sure you kind of write this down when you're under pressure, because it's really easy if you're just looking at it, so you have to put this with that and so forth. Really easy unless you've done about 100 of them to get it mixed up. And a couple of people did, but had the right idea. And it's okay. So expanding what I said here. Can't say that before. think about log base 2 of 16. You can use these relationships and you can invert this to say, okay, log base 2 of 16 equals x means that x 2 to the x equals 16. And you can just take powers of 2 until you hit 16. Okay, so 2 to the 4th power equals 16. So x equals 4. Now, you might not know the 2 to the 4th is 16. You might not recognize 16 as a power of 2. If I put 256 there, you probably wouldn't know that that was 2 to the 8th power. Okay, if I put 4096 there, you would know that's 2 to the 12th power. Okay. So we can think about the table 2 to the x. We can extend this table in either direction through the negative numbers or the positive numbers, just to get an idea of where this number, whatever it is, might be on the table. And it's a really good thing to understand the expanded table. So here we have the usual values: 1/4, 1/2, 1, 2, 4. And we all know where all those come from. Let's just go out to 3, 4, 5, 6, and we're going to get 8, 16, 32, 64. If we go up this way, go to -3, -4, -5. At -3, we're going to get 1/8. -4, we're going to get 1/16. At -5, we're going to get 1/32. Might be hard to read those, but it's real easy to figure out those numbers. It's real easy to do powers of 2. They don't get too big too fast, although they do get big pretty fast. Any exponential function does. But once we understand this table, then of course we understand the log base 2 table. And we're going to get these values. And right there, I've got them all the way down to 2 to the 7th. There's no calculation here that you can't easily do in your head. Okay, once you know you got 32, you can double 32. That's real easy. 2 times 30 is 60, 2 times 2 is 4, you get 64. 2 times 60 is 120. 2 times 4 is 8, you get 128. Okay, one way or another, there's no number here that is difficult to calculate. But it really isn't very difficult to calculate the numbers until you get up to the 13th power. Even then, it isn't that hard. Okay. In terms of this table, you can recognize both of these without having to invert the function and figure out what your power is, because you've got them all listed here. Okay, at least down through the 6th power here, and even you can see what the 7th power is here. I could actually still put 7. 128 down here, so the tables match up completely. So log base 2 of 16 for two reasons, because 2 to the 4th is 16. It's the answer to the question, 2 to what power equals 16? We got 4. Okay, what about 1/8? Does 1/8 appear over here? Well, yeah, it's a -3 power of 2. Now, hopefully you recognize 1/8 is 2 to the negative what? It means 1/2 to what power? Okay, 1/8 is 1/2 to the third. We could do this, log of base 2 of 1/2 to the third. That's log base 2 of 2 to the -3. That's -3. Totally related. The reason log base 2 of 1/8 is -3 because 2 to the -3 is 1/8. So you want to understand the arithmetic, at least for logs base 2. When you get up to logs base 3 or 4 or 8 or 12 or 16, it gets a little harder. Logs base 10 are easy. Okay, what's a log base 10 of 100,000? 100,000 is, well, it's 10 squared is 100, 10 cubed is 1,000, 10 to the 4th is 10,000, 10 to the 5th is 100,000, right? And it just matches the number of zeros. Okay. So you want to have some intuition about that. And you can make a table for your base 10 logs. That's pretty easy to do. Making a graph for base 10 logs gets out of control really fast because the numbers get big really fast, or they get really small. Okay. So one of the reasons we start with a base 2 log is the numbers stay manageable. You can visualize all these numbers. If it was a base 10, well, by the time you get out to 10 to the 7th, you've got 10 million. You can't visualize 10 million, but you can recognize it because it's got 7 zeros. Okay, but try to put it in a graph, try to put it in the same graph that you have for 10 to the -1, which would be 0.01. How does 0.01 compare on a graph to 10 million? It's ridiculous. And it's invisible. Okay. Of course, this is another reason we do log graphs, and we're going to get up to that probably later this week. Okay. So these are all important connections. Now, natural log of e squared. Okay. Okay, natural log of e squared. First of all, big deal. You just got to remember that the natural log is the base e log. Okay. Now, there are things about the number e. I've got to do a set of videos. I got to find time to do a set of videos of all the things that should be in pre-calculus courses, but aren't anymore. Things that would really help prepare people for calculus. I don't think anybody would watch them. Yeah, probably, yeah, people in other countries might, but they probably already know it. Okay, we've done this course down a little too far to fully support people who are really going to understand calculus. On the other hand, the argument in the contrary is most of you aren't ever going to take an engineering calculus course. Still, pretty important to know where the number e comes from. So if I do a set of videos on that, I expect you all to spend your Christmas vacation doing it, even though you're not required, right? No, don't do that. Okay. Natural log of x is log base e of x. So the natural log of e squared is log base e of E squared. Now, it should then be obvious what the answer is, but just in case it isn't yet. I'm glad you used two fingers on one hand. Okay, now, okay. Log base E of E squared. And yeah, we know that's 2. It helps to have a table. You can understand a lot from just this table. The pattern is really simple. So simple that I wrote it down wrong. No, I didn't. Told you I'm not with it today, and I'm proving it every minute. Okay, -2, -1, 0, 1, 2. This would be e to the -2. Okay. And it's not the table I want to make. This is e to the x. Okay. Y'all got it straight yet? I'm sorry for being confusing. Sometimes I have a little trouble distinguishing the future, which I already know, obviously, from the present. So what should be obvious, I really don't know much of anything today. But I was thinking ahead. Never mind. I was scrambling what I'm going to do with what I'm doing. Okay. So natural log is the inverse of the e to the x function. So pattern of this table matches the pattern of this table with the column reverse. So we're going to get -2, -1, 0, 1, 2, and so forth. This ought to be something you always have in mind so you understand as deeply as possible, not just on the surface where you apply the rules and get the answer without really seeing what it means. Okay, although it's important to do that too. If you want to connect everything back to the most fundamental thing, which is the table, and of course the graph. And E is a number between 2 and 3, as we discussed before, I think. Did we? I put 2 to the x in a graph, I put 3 to the x in a graph, we set e to the x is in between them. Is that in this class? Yeah, remember saying that? Yeah, so review that. And I'm not sure I did that in the other class. Okay. Anyhow, here it is. So if you want e squared, what's the natural log of e squared? Well, we could go to this table. Right there it is. Okay. So if we have a picture of this table, we know that if we have a natural log of e to the power, then since e to the power appears over here on this table, e to the power is going to appear over here on this table, and the powers are going to be what we have here. Make any sense? The natural log of e to the -2 is -2 because e to the -2 is e to the -2. It's just the inverse of this relationship. Okay, well, one way or another. Be sure you remember that the natural log is the base e log. Makes a lot of the questions much easier to answer. So if we come over here and we get the natural log of e squared equals 2. by the graph, by the table, by the inverse function relationship, right? And ultimately, it's by the inverse. I'll say by the inverse function relationship, y equals e to the x. What about the natural log of 1 over e cubed? Well, what is e to the negative 2? I don't have room to write it here, but it's 1 over e squared, right? That's how, go ahead. We got had a question or comment. Okay, so natural log of 1 over e cubed. I don't have room to write it here, but I'll write it here. What's e to the negative 2? It's 1 over e squared. Right? If I had a negative 3 in this table, I get e to the negative 3, which is 1 over e cubed. So where I've got e to the negative 2 here, that is 1 over e squared. And if I went up to here, I'd have maybe e to the negative 3, which is 1 over e cubed. Probably can't read that, but just know what I'm writing. Just going to be the inverse of this, and that gives us negative 3. So since 1 over e cubed is equal to e to the negative 3, natural log of 1 over e cubed is the natural log of e to the negative 3, and that's just negative 3. Now we had comment. We should have commented earlier while I still had space on the board. But I'm going to do it. Yeah, make us a little space down here. And you can always get the result up here. So if I want to do the natural log of 1 over e cubed, let's say I just make an equation. X equals a natural log of 1 over e cubed. Okay, that's equivalent to saying that okay, we're going to say that's e to the x and figure out how to say the conversion quickly with the it's not as straightforward. We're going to have to apply different principles. I don't know if I have room to do this. I might have to start on another board, but let's look at this. Okay. Another consequence of all this is e to the natural log of a has to equal a, because e and the natural log function are inverse functions. This is directly what it means for e and e to the x natural log of x to be inverse functions. Because remember, if you do the inverse function of the original function, you get x. Okay, you get the number you started with. So we can say then that e the x equals e to the natural log of 1 over e cubed. So that e to the x equals one over e cubed. That's the inverse function relationship. We do e to this side, we get e to the x. We do e to the natural log of one over e cubed. Well, e to the natural log of anything is not anything because we have an inverse function. So e to the natural log of one over e cubed is just one over e cubed. Then you have to recognize that one over e cubed is e to the -3, so x equals -3. That's a little more sophisticated way to do it, and it's a very good way to do it, using the inverse function relationship. And that's what you would need to do if you like had natural log of 1 over e to the 7.3, which does not appear on your table anywhere. But if you see the pattern, of course, you can see that, well, if I had 7.3 here, I'd have e to the -7.3, or if I had -7.3 over here, I'd have e to the -7.3. So if I had -7.3 here, I'd have e to the -7.3 here, I'd have -7.3 over here, okay? The important thing, the thing that throws a little bit of a curve on this one is understanding the very basic thing that e to the -x equals 1 over e to the x, right? The whole thing about the negative exponent, that people still tend to stumble over sometimes. You got to understand that e to the -3, I'm sorry, that 1 over e cubed is e to the -3 before we can do much of any of this. So, important thing to review and be aware of. Okay, well, let's solve a couple of these equations. We're going to do that. Now, when we get into this, we still want to keep our tables in mind. We still want to keep some of the basic numbers in mind, but we have 3 times 2 to the x equals 9. We want to use the inverse function relationships. We want to use this conversion, but we can't yet because this isn't in that form. Yeah, what we have to do to get this into this form, because you see, we're going to want this form because the x is in our exponent. We can get this form if we divide both sides by 3. So 2 to the x is 9 over 3, and that's just 3. So x equals log base 2 of 3. And that's your exact solution. Have the log of 3 over the log of 2. And if you have a log based button on your calculator, don't use it. Just use the LOG and the or the LN. Either one will suffice. Okay. Don't go to the expedient route of getting the answer by skipping a step, which is what you're doing if you use a log-based B button. You just totally skip something that's essential. This is exact. This is exact. calculator approximation, calculator approximation. Okay, I didn't even realize the calculators had a log-based B thing. Okay, laughing at something still up there? Oh, you got to tell me what you're laughing at. Okay. Okay, turns out people were laughing about calculators. And I said, well, I put calculators in my stew. And then, so, well, you got to plant them growing under certain conditions, but they have an advantage because the deer don't eat them. And the deer eat my tater plants. My calculator plants, they don't. So somebody said, well, do you get that by planting a calculator? And yeah, this whole thing devolves into mass hysteria, yeah, everybody laughs. I mean, I can't find words. It's not hysteria. That's an extrapolation of what it was. It wasn't hysteria. Everybody's still in their seats. No blood on the floor. Okay, so and then somebody said, do they grow square roots? Okay, well, that was pretty funny. Okay, I don't know if it comes across on the video, but it's worth repeating. Okay, that was very good. Despite my own personal difficulty finding words and saying things coherently today, it certainly lifts my spirits. Hopefully everybody else. Okay, back to the calculator approximation. We don't want to go too much further with that. There is a picture that I usually have hanging up there that y'all need to see. So I'll find that and put it back up there so we can talk about that too. Actually, I might just pull out the original. Okay. That's how we solve the equation. Second equation. E to the x squared plus 7x minus 3 equals 0. That's not 0, it's 20. There's 2 from that 0. Okay. Means that the natural log, well, x squared plus 7x minus 3 equals the natural log of 20. Natural log of 20 is just a number. Well, writing out the solution to this equation is a little bit of a pain. We get x squared plus 7x minus the quantity 2 plus the natural log of 20 equals 0. And this 3 plus the natural log of 20 is just our value of C. Well, it turns out the natural log of 20 is probably about 3.2. You can punch that into your calculator, just 20, hit the natural log cube or whatever. Okay, so we don't really want to try an exact solution to this, although we could. But we're probably going to need to approximate the solution in any case. So in this case, I say it's kind of okay to approximate the natural log of 20. What'd you get? Hang on, 3 point what? Okay, okay. So anyhow, I'm going to use 3.2. So we get approximated 3 plus the natural log of 20. And now x is -7 plus minus the square root of all this, etc., and you just plug in the numbers. Okay. If I want an exact solution, and there might be times where I want this, we need to be able to see, we just plug in. And move this board over a little further. We plug in 3 plus natural log of 20 here. Okay, there's your 4AC. And that should have been a negative 6.2 here, which of course will make this whole thing positive. So we put the positive in here. C equals negative quantity 3 plus natural log of 20. So X is going to be this. And then if you're reporting this to somebody else and you're not going to be engineers, somebody could, I mean, somebody might, but you're not going to be likely to be engineers, so you're not going to want to be reporting this to your supervisor. Okay. But if you were, you'd say, here it is, there's your exact solution, just approximate it. But then you'd probably say, just in case, here's the approximation. Okay. Report the exact solution, report the approximation. And that's probably, that's something I could ask you to do in a test. And say, go ahead and approximate it, but also, you know, 2 points out of 10, show me the exact solution. Make sense? Okay. Well, then the last one. Do it here because I want to say something up here. What 07x is a natural log of 2. Again, using this relationship carefully, we get, of course, you've got a log base E or a natural log. So you might want to remind yourself, write down log base E, but of course that's a natural log of 2. So that X is a natural log of 2, which is 0.07. And it just turns out that the natural log of 2 is pretty close to 0.7. So this turns out to be pretty close to 10. So there's your exact solution. There's your approximate solution. Now this has some real implications. Implication being that 10 is the doubling time for this. If X equals 10, well, e to the 0 equals 1. Okay. If X equals 10, you're going to get e to the X equals 2. So, well, there's doubling time. So I'm just going to comment on that and we'll do a little bit more with it. So let's go ahead and talk about doubling time. Okay. doubling time of y equals a b to the x. Now we can visualize that on the graph. A b to the x has a graph that looks exactly like y equals 2 to the x, but with different numbers. Okay, first of all, the y-intercept is 0a, because obviously when x equals 0, b to the x equals 1, and you get y equals a. So it's a no-brainer that the y-intercept is 0a. But x equals 1, y equals a times b. Okay. So here's the line y equals a times b. And right here is 1. Now, if b is a big number, like b isn't 2 here, what does it look like b is here? Show me with your fingers. What would you estimate that b is if this point is 0a and this is b times a? Yeah. What would b have to be? Okay, looking at the graph, if this is 0a and this is a times 2, which is b times a, right? What's b? Well, b is what you got to multiply this by to get this. Is what you got to multiply by a by to get y here. As an example, if a is 10, then what's this? Well, people are telling me maybe 30, maybe 40. Okay. So this is maybe 3, maybe 4 times as big as this. You want to be able to see that on a graph to estimate it. And if you're wrong, if you think it's 5, that's pretty harmless. Okay. Think it's 1/2, well, you got a problem. But this is not 1/2 of this. Okay. If you think it's 2, well, you probably not estimating very well, but you kind of got the idea. 3 or 4 would be a good answer. 5 wouldn't be bad. So I'm going to say it looks like I've got equal numbers of both 3 and 4, so maybe 3.5. So maybe this, 2 of them's here, 3 of them's here, 4 of them's here, kind of somehow splits the difference between 3 and 4. So we'll just really split the difference. Okay. Now, what's the doubling time? How long does it take this thing to double? Well, to double, it means it goes from a, let's say, to 2a. So where's the line for y equals 2a? Well, here's 2a. Here's the line y equals 2a, right? So how long did it take this thing to double? Well, between here and there, if this is, let's make this t instead of x. Let's make it b to the t, so we're thinking in terms of time. It's pretty typical to think of doubling time. That's what we call it, doubling time. Going to help to call it t. Okay, so right here's your doubling time, which I'll indicate by t sub dub. Did I use that sub dub thing last time? Anybody heard me say that before? Somebody has, but it's either in the class before this one or this. Okay, so it's sub dub, which gets us into nursery rhymes, so we're not going to get away. Okay, so I just put a T for the DOUB doubling time for doubling time. indicate the doubling time, okay? So it looks like it pretty much doubles in this time. Okay. If it's a good exponential function, if my graph depicts a good exponential function, then another doubling time would get us to here, and we'd be, if you double a doubling time, you get a fourple. Okay. A quadruple. 2 times 2 would be 4. Okay, so yeah, if you think that's a doubling, then you think this is a doubling, and y equals 2a line might be a little high, but we get the idea. So maybe 2 doublings gets us up to here. If b is 3.5, then actually the doubling time would be a little longer, so it'd be a little past 1. Take a little more than a doubling. We're not going to worry about that. That's the picture though of doubling, and that's a picture of what b to the t looks like if b is bigger than 1. Can be important. That might be important for some of your homework. Okay, well, to solve this algebraically, just looking for room here. Well, t equals 0, y equals a, b to the 0 equals a. We already used that to plot this point. At t equals t dub, then y will have doubled. Y would equal 2a. What this means then is that y this way. It follows then that ab to the t dub is 2 times a. Okay, because again, if t equals 0, y was equal to a. You see that in the picture. At t dub, y has to equal 2a. So we solve the equation ab to the t dub equals 2a. You want to try to think how this relates to the picture, because the picture helps you understand what equation to write. So what's b to the t dub? Divide both sides by a, you get b to the t dub equals 2. You convert this to logarithmic form, and you get t dub equals log to the base b of 2. And there it is. You can approximate that in your calculator. As log of 2 over log of b. That's doubling time. Okay. Now there's some properties of logarithms. We need to run through the last 8 minutes, okay? Log of A times B is log of A plus log of B. You have a rule for exponents. It says 8 of the x times 8 of the y is 8 of the x plus y. That should be familiar. Okay, so it's like you have a multiplication of two numbers to the same base, two expressions with the same base. You add the powers to get the product. Okay, here you've got a log of a product, and it's like you're adding powers. Okay, it's kind of inverse to adding the powers. Maybe okay. An unnecessary law or rule is log of A over B. Clearly, it's this. But the other necessary law is that the log of A to the value C equals C times the log of A. So I'm going to ask you to just write out some expressions. Or expressions, see what you can do with those using the rules. Let me number the rules and kind of makes that smudge. It's pretty bad on the video. For right now, we use 1, 2, 3 for these rules. Which rule applies and how does it apply in each case? Okay, people did real well with this. These rules are pretty easy to apply. And you're going to need them. A lot of the homework. And a lot of the homework goes back with inverting from one form to the other also. So just real quickly. Log of x, y is log x plus log y because instead of a, b, you've got x, y, and you got the plus. Everybody saw that. And the log of x cubed is 3 log of x. Now this is by rule 1. This is by rule 2. And then 4 log of x equals a log of x to the 4th. And this is also by rule 2. But of course, what you have here is the right-hand side of rule 2, and of course, you do the left-hand side. You write these in any order. in any case. Okay, then. Rules 1 and 2 tell you that the log of x cubed y squared equals the log of x cubed plus the log of y squared. And that's rule 1. And then rule 2 gives you 3 log of x plus 2 log of y. And I didn't see any errors. Okay. Not everybody got that last one, but I felt like everybody was going to get it. So I wanted to confirm what you got, and we have about 15 seconds left. I apologize for being a little off today, but hopefully we got the ideas across, and at least we got a few laughs. Okay, so very well done. I think you're going to be in good shape. Quick correction, somebody pointed out I had a 3 here instead of an X. Just confirming the fact that I'm not quite with it today. Okay, very good, thank you.